So we continue our journey in Chapter 7. Having just finished 7.1, unsurprisingly, we move on to 7.2. Now in this section, we continue studying inverse trig functions. Okay, remember in 7.1 we defined arcsine, arccosine, arctangent. And I said, oh, the other ones we don't worry about so much. We introduced them here. It's a pretty brief treatment. And if you are still fuzzy on arcsine, arccosine, and arctangent, it's going to get even worse here. So make sure that you have a fairly good understanding of how arcsine and arccosine and arctangent are defined and how they work and how they interact with their inverses before coming into here, because things get a little tricky. It's simultaneously less important and trickier to get through. So make sure that you've got the fundamentals down, because it's more important anyway. But if you feel good about 7.1, we'll continue with 7.2. So we're going to define inverse secant, inverse cosecant, inverse cotangent, and work with them. That's basically this section. It's a shorter section. As I said, this is actually a less important version than the last ones. Okay. What is going to come up in this section that is sort of important is what happens when you compose a trig function with an inverse trig function that aren't exact opposites of one another. So we'll see what that means. Okay. So all we do is we define arcsecant, arccosecant, arccotangent, aka inverse secant, inverse cosecant, inverse cotangent, the same way we did it before. You just have to restrict the domain so that the functions are 1 to 1. Now since secant is 1 over cosine, we're going to use the same restriction that we used on cosine. Since cosecant is 1 over sine, we're going to use the same restriction that we used for sine. And since cotangent is 1 over tangent, we're going to use, oh, no, we're not. Okay? So for cotangent, this is cosine of y over sine of y. So what we're worried about is we don't want this denominator to be 0. Okay, so we don't want sine of y to be 0. So what we're going to do is we're going to go from 0 to pi. Note for angles from 0 to pi, that's exactly sine is positive, cosine goes from positive to negative. The ratio cotangent is going to accomplish everything it can. Okay, so the domain restrictions for secant and cosecant are pretty straightforward. The domain restriction for cotangent is, remember cotangent graphed like this, it had infinitely many branches. If we had done negative pi over 2 to pi over 2, you'd be cutting it like here and here. You would get all the relevant behavior, but it's a very weird way to do it because you'd have this vertical asymptote in the middle. Instead, you cut it from 0 to pi, and you just get one branch. Okay, so that's the standard there, 0 to pi for cotangent. So find the exact values of each of the following. Arcsecant of 1, arccosecant of 2, arccotangent of minus root 3. In other words, an angle whose secant is 1, but since we're working with a secant specifically in quadrant 1 or 2. For part B, an angle whose cosecant is 2, but since we're working with cosecant, we're implicitly working with sine, so an angle in quadrant 1 or 4. And for part C, an angle whose cotangent is negative root 3, and since we're working with cotangent, we're looking for an angle in quadrants 1 or 2. So pause and try to work all that out. I'm just going to mark down. This is going to be in quadrant 1 or quadrant 2. This is going to be in quadrant 1 or quadrant 4. This is going to be in quadrant 1 or quadrant 2. So pause here and figure this out. So let's check our answers. So we want an angle in quadrant 1 or 2 from 0 to pi, whose secant is 1. Notice that secant isn't defined at pi over 2, so we don't want to get that as an answer, and we never will if we do it correctly. So theta is an angle whose secant is 1, aka the secant of theta had better be 1. And the only angle in between 0 and pi that accomplishes that is 0 itself. Okay. Also, what you could do is you could say if the secant of theta is 1, then 1 over the cosine of theta is 1. And that would tell me that the cosine of theta is 1, which is also going to happen for the angle of 0. What I do want to point out, by the way, arcsecant, not the same thing as 1 over arccosine. No. Okay. This is where the exponent version of using inverse function notation gets a little unpleasant or a little misleading. Okay. Secant is 1 over cosine. The inverse of secant is not 1 over the inverse of cosine. In more formal language, basically, doing 1 over a function and doing the inverse of a function, it really matters what order you do that in. Inverting the function and then doing 1 over, that would be 1 over the inverse sign. Doing 1 over cosine would be secant, and then inverting would be arcsecant. And those are two very different things. So doing 1 over something and then inverting it, you can't just do it in the other order and expect the result to be the same, which is why arcsecant is not the same thing as 1 over arccosine. Okay, secant is definitely 1 over cosine, but arcsecant is not 1 over arccosine. Similarly, arccosecant is not 1 over arcsine, et cetera, et cetera. Okay, part B was, let's find an angle whose cosecant is 2, but it's got to be in quadrant 4 or 1. Well, if the cosecant is 2, that means the sine is 1/2, and the angle that accomplishes that is pi over 6. So the arc cosecant of 2 is pi over 6, an angle in quadrant 1 or 4 whose cosecant is 2, aka whose sine is 1/2. Okay, part C. I don't remember there being a part C. Oh yeah, there was. Sorry. Now, it was all like 30 seconds ago, and I've forgotten. So we want an angle whose cotangent is -√3, but specifically an angle in quadrants 1 or 2. So if we want the cotangent to be -√3, the only angle that accomplishes that, just looking at our sort of standard reference, is 5 pi over 6. So the arc cotangent of -√3 is 5 pi over 6. Can we approximate these values? And again, as we saw with arcsine and arccosine, there are some things we can work out exactly, but for a lot of stuff, we're just going to plug it into a calculator. Okay? So arcsecant of 8, arc cotangent of 1/5, arc cosecant of -2, arc cotangent of -1/2. This is really just a matter of plugging it into your calculator. And then be careful if you're in degrees or radians mode. Now here's a question for you. Okay? Does, suppose we get x equals, let's say y is arcsecant of x. Does degrees versus radians mode affect x or y, the input or the output? Arcsecant x means an angle whose secant is x. So between x and y, which of these is the angle? This is. So when you're doing sine, cosine, tangent, etc., the input is affected by whether you're in radians or degrees, because you're taking the sine and cosine of an angle. Arc, cosine, arcsine, those are spitting out angles. So changing to degree versus radians will change the out of those functions. So if you're in degrees versus radians mode, arcsecant of 8 will be two different things. Okay. By default, you should always be in radians mode unless you are very clear that you're working in degrees. So this is just a matter of punching into the calculator once you're in radians mode. Okay, so arcsecant of 8 is just an angle whose cosine is 1/8. The point being, a lot of calculators don't have an arc cosecant or arcsecant button. I should have been clear about this when this example started, sorry. If your calculator has an arcsecant button, by all means, just use it. Otherwise, you're saying, I have something that is the arcsecant of 8. That means the secant of y is equal to 8. That means 1 over the cosine of y is equal to 8, aka the cosine of y is equal to 1/8. So your actual answer was the arc cosine of 1/8. Okay. Notice this interesting relationship. Okay. The arcsecant of 8 is not 1 over the arc cosine of 8. It's the arc cosine of 1 over 8. Okay, so there's an explanation for what they just did, in case you don't have an arcsecant button. Well, instead of arcsecant of 8, you would do arc cosine of 1/8. And that produces about 1.45. Okay, what arc cosecant of -2? Again, let's presume you don't have an arc cosecant button. Many calculators don't, because you don't really need one. If I set y to be the arc cosecant of -2, I'd say the cosecant of y is -2, which means 1 over the sine of y is -2. So the sine of y is -1/2, and therefore y is the arcsine of minus 1/2. And we have that similar relationship we had in the last example. Instead of doing arc cosecant of minus 2, you can do arc sine of minus 1/2, not 1 over arc sine of minus 2. You do the arc sine of negative 1/2. So I'm going to clear out my work because the book is going to write all the same things. So again, we end up with the arc sine of minus 1/2, which you punch into a calculator in mode will be about negative 0.52. Okay, part C, arc cotangent of 1/5. Again, you probably don't have an arc cotangent button. So this will be equal to, try to guess the pattern, this will be equal to the arc tangent of what? So pause here, work through it, make a guess, work through it, see if your guess was right, try to come up with an answer. Okay, moving on. This is an interesting way for the book to do it. I wasn't expecting this, sorry. They're going outside the unit circle and ending up with an answer of 1.37. That's fine. Let me go back and do it the way I was sort of expecting, similar to how they had done it. So if I let y be, they've actually let theta be the arc cotangent of 1/5. That means the cotangent of theta is 1/5. Now, if I reciprocate this, what's 1 over cotangent theta? It's just tan theta. So then I would find theta is the arc tangent of 5. Okay, and generally calculators will have an arc tangent button. So the way they solved it, just to work through it, was they said, I've got an angle whose cotangent is 1/5. I'm in quadrant 1 because I know that my x and y coordinates are both positive, because the ratio of them was positive, and in quadrant 1 that'll happen, but in quadrant 2 you'll end up with a negative ratio. So since the cotangent of theta is positive, and I know theta is either in quadrant 1 or 2, I must be in quadrant 1. So what I have is I have an angle theta, I have an x, I have a y, and I'll put this in a circle that isn't the unit circle. Let's just call it a circle of radius r. Then cotangent of theta, pardon me, is always y over x. Oh, no wonder it looked so weird. The vertical is usually labeled with y, and the horizontal is usually labeled with x. So cotangent is x over y. So I can go ahead and declare, since the cotangent was given to be 1/5, let's just let x equal 1 and y equal 5. By the Pythagorean theorem, we get r is equal to 26, the square root of 26. So I'm going to clear some stuff out. Using theta is the arc cotangent of 1/5, then we got the cotangent of theta is 1/5. We drew a quadrant 1 solution in a circle of an unknown radius, which turned out to be root 26. Since the cotangent is the x over the y, I called this 1, I called this 5. Okay, and now here's our angle theta. It's an angle whose cotangent is 1/5. And from there, we're trying to find what is theta. But then you can do things like say, well, the cosine of theta is 1 over root 26. And then I can just take the arc cosine of that. Okay, I think this is more confusing than just taking the arc tangent of 5, but whatever. Sorry, I'm just breezing through there. So there it is, 1.37, and there you see it, the arc cosine of 1 over root 26. Okay, how about arc cotangent of -2? So actually try to do this 2 ways. Try to do it using their convoluted, what quadrant am I in, let's make a circle and draw a triangle, and then just try to do my inversion method. So pause here and work it out, preferably twice. So cotangent being negative means I'm in quadrant 2. Cotangent is the x over y, so we're going to label the x1 and the y2, which makes the radius root 5. Then we can understand that the cosine is -1 over root 5, from which we can take the arc cosine and get 2.03. So let me go back here Why did the book use cosine of theta is -1 over root 5 rather than sine of theta is 2 over root 5? Sorry, lawn care people. So why did they go with this rather than this? And the answer happens to be, we already know we're looking for something in quadrant 1 or quadrant 2. Between the arc sine and the arc cosine, which one of those is going to guarantee a result in quadrant 1 or quadrant 2? Arc cosine will. So this might end up leading me astray, but arc cosine will eventually get me the right answer. So they're using cosine here because later we're going to take an arc cosine, and arc cosine already produces something in the right quadrants. Okay, the other way you could do this, pardon me, let me get all their text away, would be to say, oh, theta is the arc cotangent of -1/2, therefore the cotangent of theta is -1/2. If I reciprocate, I get that the tangent of theta is -2. So theta is the arc tangent of -2. Now I'll admit, I have to put an asterisk here, because arc tangent produces angles in quadrant 1 or quadrant 4, but I wanted something in quadrant 1 or quadrant 2. And actually, in this case, we know the result is going to be in quadrant 2. So what would happen here, so here's a downside to my perhaps simpler technique. At the end here, you're going to end up with a negative something or other. That tells me I'm in quadrant 4. However, my result was supposed to be quadrant 2, so what you have to do is reflect it across here. Because remember, tangent and cotangent have a period of pi. So if I just add pi to it, I will have taken my angle that was in quadrant 4 and moved it to be in quadrant 2. So the technique I showed involving this simple reciprocation, you do have to be careful about what quadrant you're going to produce. Which, to be fair, the book's technique also required. It's why they used cosine here instead of sine, because arc cosine is going to respect the same quadrants that arc cotangent did. Okay. So that's it for this video here. In the next video, we'll come back and we'll keep working through various examples. But specifically, we're going to start composing trig functions with inverse trig functions that aren't the same trig function. So come on back for the next video and we'll see how to work through that.